Hi, and welcome to Intro to Data Analysis with R. My name is Pri Oberoi, and I'm a data scientist at the Commerce Data Service within the U.S. Department of Commerce. So before we get started today, if everyone could make sure that they have gone to this GitHub repo and downloaded all the content that they need for this class. So once you open up the repository, there's some instructions in the README on how to go about getting the content in the repo, but it should be pretty straightforward. If you're comfortable with the command line, you should be able to clone the repository right here, or you can just download a zip file of everything and unzip it and start to get going. Here's my contact information. If you have any questions related to the content of the class itself, feel free to reach out. If you have any questions about Data Academy, the series of classes, registering, any logistics, please email us at dataacademy@doc.gov. So my goals for this class are for everyone to walk away with the foundations for what the role of data analysis is in the data science pipeline, how we're going to use R Markdown to create code that is, one, to have code that we're going to follow along with in class, but also create code that allows you to make reproducible data analysis pipelines. We're going to look at data visualization and how you can use it to clean data and aggregate and summarize data. And we're also going to look at some statistical tests and how to go about testing the hypotheses that you have made about your own data set. So the data science pipeline, more of a cycle, but it begins with that ingestion phase, cleaning your data, wrangling it, kind of getting it in the right shape, doing analysis, modeling your data, and then developing reports or applications or whatever, and then closing that loop so that that last step results in more data that can be ingested. So the steps in the data science pipeline are certainly not one-directional, and they're not particularly discrete. So as you begin ingesting your data and cleaning it and wrangling it and doing analysis, you may decide along that pathway that you want to do some sort of unsupervised learning technique on your data. You want to do k-means. And as you do that, you realize that your data had missing, a bunch of the variables that you would like to cluster on have missing data on them, and that you may have to impute that missing data, and that might force you to go back to that cleaning step and wrangling and doing analysis again and seeing whether the imputation method you picked was appropriate for the modeling method that you've picked. So this is certainly not one-directional, and as you'll see, analysis plays a step as you are going through each of these. So let's begin with why we actually do data analysis. Right, analysis isn't its own step, and when you're doing data science, and you use it when you're cleaning your data, when you're wrangling it, when you're describing and summarizing kind of what's going on with your data to someone else. You need to communicate that, and you also use it to inform what machine learning methods you use, and what you actually can use. So you'll use analysis throughout the pipeline. Which means today we're going to focus on analysis for cleaning, wrangling, and summarizing and getting ready for that modeling component. I'll pause here because we need to make sure that everyone is comfortable with our Markdown before we go forward. All of the content for this class is, all of the code for this class is in an R Markdown file, which you should have been able to find when you went to the repository and downloaded all the content. So there's one file that has an extension, R Markdown extension. You can open that up in RStudio, and it'll look like this. If you have any issues running the code right now, or if you want to just follow along while you're listening to this class, you can open up the HTML, and you'll be able to see all of the code in chunks, and also what the output was from the code. So as we saw, our Markdown allows you to make output in as HTML, but also PDFs and Word and HTML5 slides and things like that. So there's a lot of benefits to them. It's very easy to create, and you can embed chunks of R code throughout throughout your R Markdown, including and as well as text, and put formatting and things like that, and images to make it more readable. And also, your chunks of R code are either visible or not on your final output. That's kind of up to you, and you can make decisions on whether or not warning messages and things like that from code actually appear in your output document. And I think two of the more important components of R Markdown and how I leverage R Markdowns is that it allows you to add a narrative through your code. It allows you to break up your code and talk about what's going to happen next or what you just did. And it allows people to understand what it is that you've developed. And the second is that R Markdown allows you to write code that is reproducible by someone else. So when you run code in an R Markdown, you create the HTML output by knitting your R Markdown. The environment that your R Markdown uses is distinct from the environment that you use in R scripts and just like in the console, which means that if you load a library using the library command in your R console, but don't do that in R Markdown, and your R Markdown uses that library, like ggplot2, you'll get an error message and it won't produce the output. So what that means is that you know that if you are producing an R Markdown file and you've managed to successfully knit it to produce the output you want, that all of the code that's in there, or all of the commands that you run in your R code, will be reproducible by someone else if they get access to that R Markdown. So here's a little bit of an anatomy of not just the R Markdown file, but also the RStudio environment. So here you can see we have the data analysis with R Markdown open. Here is the gray bar, the code in gray are each code chunk, and you can run the code in each chunk using this run button, or you can select one line or multiple lines and hit Command Enter on your Mac. You can also navigate between the chunks using this drop down. So you can see this is chunk 1, and you can select this drop down to navigate to a different chunk. And then any output, console output will appear in the console. Any data frames or other objects that you've created will appear in your environment. And of course, any plots that you run will appear in the Plots tab. So when you knit HTML, for example, when you create HTML output using your R Markdown, all of your plots and your text and the code that you choose to appear will all appear in a new window together. But if you run individual lines or chunks or anything like that, you'll see the output appear on the console or in the plots or the view or in your environment. So our analysis toolkit is kind of made up of visualization, looking at statistics, and aggregating your data. And so I'm going to begin with the data visualization component, since it can provide a lot of insight into what's going on with your data. So if you attended the Intro to R class, we used the ggplot2 library, but we used the quickplot or the qplot function, and today we're going to hop over to ggplot. So qplot is very similar to base R's plot function. It generally has a little less typing, but it's also less customizable, and it can be a little bit harder to read in my opinion. ggplot is much more customizable, has quite a bit of functionality, and it allows you to leverage how this library thinks about the visualizations you're creating, and it kind of allows you to break out the graphics layers. So, and we'll go into that in a moment. So here are these two bits of code produce the exact same output, but one uses qplot and one uses ggplot. So you can see here on the left how qplot defines the x and y variables, so does ggplot, what the data is, and then you add on, in one line in qplot, you add on the aesthetics like the point size, the alpha or the transparency, and what the title of the plot is. For ggplot too, for ggplot function, you define your data in x and y axis, and then you add a layer for what kind of plot this is. So this is a scatter plot using geom_point. What the size of your scatter plots are, what the transparency is again, and then another layer for defining what your title looks like. So this is generally a little bit more readable. So we're actually going to toggle over to our Markdown now and get going so that we have this code running as we go through each of these steps throughout the class. So when you open up your R Markdown, the first thing you'll notice is that you have this first line or your first chunk rather, which has you install some packages and load these 3 libraries. Hopefully before the class you have installed these 3. If you have not, go ahead and just hit run to run this entire chunk of code. I already have those packages installed, so I'm just going to select these lines and hit Command Enter to load ggplot2, reshape2, and rmisc. Next, we're going to go on to the visualization component, or our next chunk. So you see when I click into this updates to chunk 2. So qplot, I'm going to run our qplot code and the ggplot code that we just talked through. And as you can see, there are no plots or anything that I've loaded. That's because we actually stored each plot to a variable, P1 and P2. So I'm going to run this line so that we can see both of them next to each other. As your plots are loading, one might load before the other. You can hit zoom right here so that we have a larger version of the files showing. So you can see the two look remarkably similar. Here's our qplot, here's our ggplot. Just the code for actually building these look different. So I would encourage you now to pause, make sure that you run the code in chunk 2. You may have to run it piecemeal to see all of the output as you go. And then I'm going to ask folks to update that ggplot code so that the color of the scatter plot points varies based on the value of the cut. And so we're going to use the color argument to the aesthetics mapping to do that. So since this is a recording of our original class, I'm going to go ahead and do this component with you. So this next bit of code here is actually just a quick look at what your ggplot function looks like when you add a loess smoothed fit curve with the confidence regions showing. So this is you can see what we did here was add one more layer to the previous code, and we did this by adding a plus symbol to tell R to look at the next line, and then added geom_smooth. So take a look at that. Here's a loess fitted curve for our data. We could also decide that we want not just one plot, but multiple plots for each of the values for the diamond cut categorical variable. And then we add one more layer to the existing code, which is the facet_wrap, which defines that each plot is going to be based on the value of cut, and it defines the number of columns in the final output of your plot. So 3 means that you should see 3 plots per line. So we have for each value of cut, which is fair, good, very good, premium, ideal, we have a different plot with our lowest smooth curve and our scatter plots. So our activity during this time is to update this last plot so that the color of the scatter plot varies based on the value of cut, right? So I'm going to copy this code right here so we don't have to type all of it out again. And I'm going to add the color argument in the aesthetics mapping. So after we define our y variable, I'm going to say color equals cut. I believe this actually does work if you spell it the American way, but ggplot was developed by Hadley Wickham, who is from New Zealand. So you'll notice that a lot of the code has color spelled that way, without quotes around them. So if we run this again, we get a different color for each cut, which is handy if they were all on the same plot as well. So you want to be able to, on the same plot, tell the good from the fair. Next, we're going to look at the next code of chunk, the next chunk of code, and look at the histograms and bar charts. So, histograms and bar charts, they're pretty straightforward. The change in code is pretty straightforward from our last set. Instead of geom_point, we're using geom_bar to define that this is a bar chart, and you can see here how I've defined the x variable but not the y. And when you do that, it'll assume that y is the count of rows. So if we run this, actually let's run this whole set of code. So we have one bar chart and then one histogram, which allows you to, it allows you to define the bin width for your x variable, so for price, which we've set to 500 here. So we have a bar chart in our histogram. You can change the bin width for the histograms. So we could set that to a higher value, like 1,000, and see what that looks like instead. And then we're going to look at box plots and violin plots. So box plots, I think most folks are familiar with them. They're pretty widely interpretable. Violin plots are actually really helpful. They take a minute more to understand because we don't see them as often, but they're really helpful for when you are not making the assumption that the values in your variable have normal distributions. So you can, if you have like a bimodal distribution of all of the values in price, like there's a peak at 500 and a peak at 10,000. You'll be able to see that in a violin plot, but not necessarily in a box plot. And then the other component of that, which we'll see, is that you can have the output for the violin plot scale to the number of observations you have. So if you have price for only half of your data, you'll notice, or rather, if you have many more diamonds of one kind of cut but not the other, you'll be able to see that in your violin plot. So let's toggle over here, and our box plot is created using geom_boxplot, and I can run that. Our violin plot uses geom_violin, and you can see here I set this. You can leave the parentheses empty, or you can set scale to count, which means I want to be able to see the difference in the number of observations we have for each of our values of cut. plot that. And you can see here how it's a little difficult to tell that there are actually far fewer fair observations in our data set than there are ideal, but it's hard to tell that with the box plot. And also you can see how there is, you can see this peak in distribution here for ideal that kind of gets washed out when you're looking at this data, or you're looking at the box plot for ideal. So as we go forward, we're going to use a data set from NTIA in their data set on broadband data that's available or for Washington, D.C. From June of 2014. And we're also going to use this data to enter the kind of statistical testing component of our class. So hypothesis testing is a concept that you should be very familiar with when you are looking at data and when you're making assertions about that data. So when you have a null hypothesis, your goal is to disprove or to see if you can disprove that null hypothesis. So in this example, as we do our hypothesis testing, our null hypothesis is that the typical upload speeds and download speeds for broadband providers in Washington, D.C. are the same as their advertised speeds. So any speeds we see for upload and download, actual speeds we see, are pretty much the same as the advertised speeds that provider has said that they provide. So if we're able to disprove that, we get to the point where we can say, yes, there is a difference between typical and actual speeds. So we're going to toggle back to our markdown. We're going to import the data by running chunk 5. And then we're actually going to take a look at that data frame and kind of get some high-level understanding of what that data has in it. If you want to go take a look at other data sets from NTIA for the broadband data, you can follow this link right here. But first thing we're going to do is load the data using the read CSV. Here's our data set. You can see it populated in the environment component part of our studio. So we want to take a look and see what's actually in there. Just looking at our environment, you can see that we have 150,000 or so observations. We have 15 variables, but we want to get a little bit more information about it. So first, let's just take a look at the first few rows. To do that, the first few rows and what variables the first few ones are. To do that, you can either click on this, click on your data frame, or you can type in view data, which is what ran for us when we clicked on it. So you can see we have, we are only seeing a subset of the rows here. And we have a couple of variables that include things like this identifier, the provider name, the doing business as name, and that sort of thing. If you want any more information about the variables themselves, the zip file you downloaded from GitHub includes a README for the NTI data, which describes some of the data sets, or some of the variables. The next thing we want to do is, if you didn't look over here, you can find out what the dimensions of your data set are by using dim data, which tells you that you have 149,808 rows or observations, and then 15 variables. You can also see what all of the actual variables that you have are. So if we type in names and data, you'll see what the name of our columns are, including FRN, typic up, typic down. You can also get an idea for what the general structure of your data set is, which is a really helpful thing to do. So if you use str data, you can get an idea of what each of those variables that we just read the names for actually are. So you can see FRN are integers, provider name is a factor that has 6 levels, so 6 values. Same for doing business as name. We have numbers and integers and other factors as well. So, oh, and then we can also do a quick summary of the data. Which will give you a little bit more information about especially for the numeric variables, what kind of values you're seeing. So you can see for FRN, it starts here. Here's our minimum value or a maximum value. For provider name, it tends to give the first few values for that factor and give you a count for that value. So there are 39,000 or so rows that have AT&T Mobility LLC. Same for doing business as name. And then you can also get an idea for things like spectrum, which is scaled really different than everything else because it's a numeric, it's a number, but it starts at 1 and ends at 6. So our next goal is to create a histogram of the maximum advertised download speeds, which in our data set is the max add down. So what we're going to do is create a ggplot, pass in our data, which we called data, and then in the aesthetics mapping have x be our max add down variable. With new data that you're using like this, it sometimes does help to just copy over the names of the variables, especially if they have some tricky spelling like that. And because this is a histogram, we don't need to define the y-axis. Use the plus symbol and use geom_histogram. Oops. And I use tab to autocomplete that line, and you can see here it's giving you, there's a little guidance that RStudio provides on what arguments you can pass to geom_histogram. But what we're going to pass is bin width. And actually, I'm not entirely, let's see, max add down had values ranging from 3 to 7. So doing a bin width of 30 or something would not really make sense. So I'm just going to say a bin width of 1. And we can add our title. So we can see that there's a spike for advertised values of 7. You can take a 10-minute break now during the live class. We use this time to answer any questions. Feel free to pause the video and come back. Now's a good time for a break. But we're going to keep going forward. So next we're going to look at using data analysis to clean data. So in order to do that, we first kind of need to get an idea of what messy data actually is. So Hadley Wickham, the content that we're going to cover is from a paper by Hadley Wickham on tidy data. That's actually a very interesting read, and the link for it is here on your slides. So some signs that you have messy data are when the column headers are values and actually not variable names. And we're going to go through examples of each of these in the data set that we have. The next is that we have multiple variables that are stored in one column, or we have variables stored in both rows and columns. And then you may also see instances where there are multiple types of observational units that are stored in the same table. And maybe that's something you're okay with or not. And then on the other side of it, a single observational unit is stored in multiple tables, which is something you might see if your data is split between multiple CSVs and you import them all separately, for example. So let's look at that first one. Column headers are values and not variable names. So if we look at our data, the max add down, which is the maximum advertised download speed, the maximum advertised upload speed, the typical download speed, and the typical upload speed. Those are all stored as different columns or variables rather than different values, right? So now we're going to run chunk 6 and use the melt function to address this issue with our data. So let's take a quick look. Max add down, add up, typic down, and typic up. If we look at our data set, these are 4 variables that all store the speed that this particular provider has either advertised or we have observed. So we're going to use melt to ensure that the provider name, we're going to use this melt function. So melt is a function that converts columns into rows, and it's something that, while can be kind of hard to wrap your head around the first time you use it, is a really valuable function to understand. And so if you want to read more about it, so if you want to take a look at the documentation for melt, you can use that command and look at the help page that shows up. But for our means, for our purposes, we need to ensure that the provider name is used as a factor. So melt will actually recognize it as a variable that it can use as an identifier. So what we're going to do is make sure data prov name well, first we're going to actually test if it actually is a factor. So to do that, once we can use the isFactor command, and you can see that that's true, which is great. If it were not, we would update this to coerce data prov name into a factor. Next, we want to make sure that max advertised download, upload, typical download, and upload speeds are numeric values. So I'm going to take a quick look again at the structure, but instead of looking at the structure for all the variables in our data frame, I'm going to specifically look at these columns. So as you can see, prov name is a factor, which is great, and then these 4 variables are integers, which are numeric. So now we're going to create a new data frame called data clean and use our melt function to, on the prov name, DBA name, and then the other variables in our data set. And you can see here it says it's using prov name, DBA name, HOCO name, and the end user cat as ID variables. If you want to take a quick look at what that data looks like, if we open up data clean, we now have a variable called variable that stores whether the speed is max add down or typic up, and then what the actual speed is, or the value. So let's create a quick plot of our variable column and our value column and see what our data clean value has in it. So maximum advertised download speeds and typical download speeds. You can see the variance in the number of values that we have between the first and third quartile are a lot larger in the typical download versus the advertised download. And generally, the advertised download is higher than the typical download speeds. So now we have one column that indicates what kind of speed we're looking at, if it's the advertised or the typical, and if it's upload or download, and then what the actual speed is using the melt function. Our next kind of messy data is when there are multiple variables that are stored in one column. So data underscore clean now has one column named variable, and it contains that variable which indicates if it's advertised or typical, as well as whether it's upload or download. So it'd be really great to be able to break that out a little bit. So we're going to go run chunk 7 and look at the data frame that shows up. But what we're going to be doing in chunk 7 is creating a variable for speed direction and speed source. So we're going to create this speed direction variable and just have all of it show up as download. And then go back and for every instance where the speed direction observation, where our variable value is either max add up or typic up, we're going to indicate that that's actually an upload speed rather than download speed. And then we're going to do something similar for advertising, or for our advertised versus typical. And then we're going to go ahead and get rid of the variable column, which was what melt created for us. So if we take a look at our values now, so with multiple variables that are now stored in one column, we have this column named variable that has indicator of whether the speed that we're looking at is a download or upload, advertised or typical, and it'd be great to break that out a little bit. So we're going to use chunk 7 and create a variable for speed direction and assign it all download, and then go back in and update the ones that correspond to advertised upload or typical upload to upload. And we'll do the same thing for our speed source variable. And then we're just going to go ahead and get rid of the variable, the column named variable, by assigning it null. So if we take a look at this data, you can see we have two variables, or we have the speed source, which is one of the variables we created, which can either be advertised or download, or the speed direction, which can be download or upload, and then values for that. So we can see that for download speeds, advertised tend to be higher than typical, and same for upload speeds. Next, we have variables that are stored in both rows and columns. So our data set doesn't have an example of this problem, but here is one, right? We have a weather data set, and there's a column for every possible day in the month. So this is day 1, day 2, day 3, so on. So our variables are individual columns, like the ID, the year, the month, and they're also spread across columns, because we should have variable with D1 all the way through D31, and across rows, because we have the tmin, tmax component. The next kind of problem is if we have multiple types of observational units in one data table. So our data underscore clean actually does have that problem where we have multiple observational units. When we look at, and a good sign that you have this problem is if you see the same value repeating multiple times in a particular variable. So if we look at the provider holding company, we'll see Selco partnership repeated a whole number of times. And so one way to think about this is, one, it's very similar to database normalization, and it isn't always true that you may want to fix this kind of messy data. we'll actually see going forward that for our purposes, it's a little bit handy to leave this kind of denormalized table in play, since that allows us to do counts really easily, and for a few other reasons. But so some data analysis tools do work really well with denormalized data. And then we might see a single observational unit that's stored across multiple tables. And so there are a couple of good functions for being able to combine them. If you have two data frames and they have all of the same columns, the same number and the same columns, you can use rbind to row bind them together. You can use column bind if there are two data frames and then they have the exact same number of rows as well. And merge is a handy way to combine two data frames using an identifier column, like a primary key. You can kind of think of it. You could also use it if you ever find yourself wondering if there is something similar to VLOOKUP that you would use in Excel. Merge is a good alternative in R. And then from the plier package, you can use ldply to read multiple CSVs into one data frame so that you're kind of combining them as you import the data. So those were a few ways that we could clean up our data, but let's look at summarizing data within groups. So we had our box plot that indicated advertised and typical speeds and showed how they may differ both when you're looking at upload and download speeds. So a handy function for summarizing data within groups is the aggregate function, which will run any function you pass it over a group that you specify. So a good thought exercise here is thinking about what, before we get started, thinking about what this line of code does right here. And what we're doing is looking at the data clean data frame and specifying that we only want to see rows where the speed direction is download, and from the rows where speed direction is download, just give us the corresponding value. So if you were to run aggregate on all of the values for download speeds, we could decide to run mean over each of them and get our main values. So let's take a look at chunk 8, so we can look at that example and also mean upload speeds. So here we have aggregate. We're running it on all of our download values. And we can see how for group 1, which is advertised or typical, we have a mean speed of 5.3 and a mean speed of 3.3. So if we wanted to do something similar for the mean upload speeds by speed source, we could replace the download value and run this line again and look at our two mean advertised and typical speeds. This is a good point in the video to pause if you need to take a break. So we looked at data visualization, cleaning up our data, kind of looking at some summary statistics by group in data, and now we're going to look at correlation. So something that we do expect is that the advertised and typical speeds are correlated, right? So as the advertised speed by any given provider increases, their typical speeds should increase as well, even if the mean typical speed is actually lower than the advertised speed, like we saw in our last example. So if we look at chunk 9, we can do a quick scatter plot to take a look at our X and Y, which are maximum advertised download and typical download. And as we expected, there's a somewhat positive linear relationship. But as we saw here, there are a couple of things that, because a lot of our values have the exact same value, we're actually not seeing all of the spots where we had a typical download speed of 0 and a maximum advertised, or maximum, or an advertised download speed of 5. We actually don't know how many spots, how many values we have right there. So first of all, we're going to add a jitter to our scatter plot so that we can take a better look at how many points we're actually seeing at that intersection. So you can see here we actually have a huge number of values, so much so that this is basically just a dense block. The only one where we see a little more, fewer incidences at this 4 and 5 intersection. So a good way to actually test out whether what we're seeing in this correlation is valid is doing a quick correlation test. In a correlation test, using the core.test function, we're passing in our maximum advertised download speed and setting y to the typical download speed. And we get a whole bunch of data back. So we get the t-value, the degrees of freedom, and the p-value, which is very helpful. So the p-value is far less than 0.05, and so if our null hypothesis is that the correlation is 0 between the two of them, then our alternative hypothesis is that the true correlation is not equal to 0, that there actually is a correlation there. So we have a correlation value of 0.5 and a p-value of less than 0.05. So we can say that there actually is a correlation between those two variables. But let's go back to our original hypothesis. So our null hypothesis is that the typical upload and download speeds for broadband providers in DC are the same as the advertised speeds. When we looked at our data and we compared our samples, it really didn't seem that way. So let's do a quick t-test to see if that difference that we kind of saw visually is actually statistically significant. And to do that, we're going to use the t-test function. The t-test function is set up to pass in arguments so that you pass in the response variable, and then the rest of your variables, one or more, and then what data you're using. So what we're trying to see is if the download speed differs based on whether the speed was advertised or typical in our data set. So our response is just the speeds, are the various speeds, and our variables are the variable that we're passing it is whether or not it was an advertised or a typical speed. So we're going to go ahead and run chunk 10 to see what we get. You can see we're given a bunch of data here. One thing that we do see is that we have a p-value of less than 0.05. You can see what our alternative hypothesis is, and we can also see what the mean in our group in our advertised group was versus the mean in our typical group, which we saw earlier as well. So this allows us to refute our null hypothesis and assert that, yeah, there is a difference in the speed, at least in the download speeds, if it is an advertised speed versus an actual speed. So we want to do the same thing, but look at the to see if the upload speeds are the same between advertised and typical. We can see we also get a small p-value, much less than 0.05, and we can see our mean values for each of the groups of our samples. So the last part that we talked about using data analysis for was for model selection and feature selection. So a scatter plot matrix shows you the relationship between your all of the continuous variables in your data. And so here we have our maximum advertised download speed, advertised upload speed, typical download, typical upload, and the spectrum variable. So as we expect, these are the names of our variables. This is symmetrical, so all of the plots on the top right are the mirror images of the plots on the bottom left. But if you just want to look at the top, along the top right, we can see how as the advertised download speed increases, so does the advertised upload speed. As the advertised upload speed increases, so does the typical download speed, etc. The only place where we really don't see any relationship between our variables is with spectrum. So I guess generally, I'm not seeing anything that says that as there's a relation between spectrum and any of the other 4 numerical variables. So a linear regression is something that you could use if you do see a positive or a linear relationship between 2 of your variables, such as we saw between the advertised download and the typical download speeds. Whereas when we looked at spectrum and typical download, we didn't really see a linear relationship there. So we might assume that a linear relationship or a linear regression might be more appropriate for looking at predicting download advertised speeds or typical speeds from each other than it would be using spectrum. The other thing that you may have to do when looking at all of the values that you have for your variables is to see whether that data needs to be normalized, and also if you have a lot of missing data. So for this example, we're going to get a data set on injuries. All right, so let's import that real quick. And you can see we have about 160,000 observations, 21 variables, and these are case numbers and various injuries for individuals that were brought into an ER. So if we look at some of our numerical variables as a violin plot, you can see the weight, the PSU, the age, the length of stay. And what this tells me right here is that we need to normalize our data so that the length of stay is roughly on the same kind of scale as our other variables. And once we do, we'd be able to begin the modeling process. So we know that we have a lot of variables in our data set, a number of factors and numeric ones. We know that our continuous variables, by looking through here, we can see we have continuous variables with PSU, weight, age, and length of stay. We can store those all in the continuous variable. And we can use melt so that we're creating a data frame of all of the continuous variables so that we actually have the variable name as a categorical variable. If we take a look at dataset 2, the variable name is now stored under variable and the values are under value. That allows us to create our violin plot and see this need for normalization with these continuous variables. In order to normalize our data, first I'm going to go ahead and create a copy of our data set. And using this for loop, I'm going to go through each continuous variable in our data set and use the scale function to normalize it. So if we melt that data again to look at our violin plot, we can now see a somewhat scaled version of all of our variables. So what we covered today was looking at, this last part was looking at these statistical tests, doing kind of visual diagnostics, but those statistical tests are different from statistical learning, right? Because we can use statistical tests to actually to help you describe your data and make assertions about your data, whereas statistical learning allows you to make more predictions into the future. So a good way to think about it, and this is a data mining map that you can follow the link for right here, but we have kind of the component, we have explaining the past versus predicting the future. And our statistical tests fall in the bin of explaining the past, whereas statistical learning or machine learning involves predicting the future. And statistical learning allows us to ask questions like, can we actually go ahead and predict what the typical download speed will be for a given provider if we know what they advertise that their download speed would be? Or we could say, if we know the upload speeds, can we generally, the advertised upload speeds, can we predict what the actual upload speeds are going to look like? So if you're interested in that component, I would invite you to come to our machine learning classes at the Data Academy so we can start looking at that statistical learning component as well. To close out, we have a couple of resources to share. We'll have these resources, we'll have these slides and the recording for this class posted on our GitHub page, as well as the Data Academy website. And if you have any questions, please email dataacademy@doc.gov.